Hey, what's the crack? How are you guys? Hey, Mohammed. Hey, Free Palestine. Can you guys hear me okay? Hopefully it's a yes. Just let me know in the chat if everyone can hear me okay. Hey, Pranav, what's crack? How's A-level physics? Can you hear me okay, Pranav? Just no one said yet if it's okay. I just wanted to make sure I've got the mic connected correct. Yes, grand. Thank you, Pranav. Thank you. So, Pranav, are you thinking of doing A-level physics? A-level physics is honestly the exact same as math, I would say, or maths, sorry, maths. So do you know how in maths it's a lot of formula, a lot of applying equations? It's the exact same with A-level physics. So do you know how in GCSE physics it's kind of more like you get an equation? So say it's like W equals mg, and you just have to put the numbers in. In physics for A-level is a bit more complicated because you'll have maybe two equations and you're trying to combine them. For example, one equation right now that we're doing is Young's modulus is stress over strain, which is force per unit area, divided by change in length over original length. And you need to be very quick at able to be saying that that's the same thing as change in length times an area, and then very quick at able to rearrange for force and say that force is E change in length area over L. So it's a lot more of using just letters, like a kind of a lot more manipulation with algebra. So it is. But I would say if you really enjoy math, you'll really enjoy physics. Maths, if you enjoy your math class, you'll really enjoy physics. But yeah, I think as a big step is there's a lot more maths knowledge in A-level physics than there is in GCSEs. Sophia, momentum questions. Yes, I can. Moments questions. So, hello, yes, Pranav, you get a massive list of equations. You get like a booklet that's basically like 5 pages long, 5 pages double-sided. However, you only get roughly 1 minute per question in your exam in A-levels to answer. So if you haven't learned the base equations, you're going to find it really difficult to do it. And a question in gravitational fields. Yeah, 100%. So maybe we could do one on moments first. So moments is equal to force times distance. Okay, so like a common moment question would be maybe that we have a table, and on that table, maybe we've got a computer sitting on our table, right? So here's my computer. I'm very bad at drawing computers, but that's a computer. And it might tell you that the table is uniform. Okay, so let's say the table's got a uniform mass of 5 kilograms. Let's say it's got a length of 10 meters. And let's say that the computer has got a mass of, let's say, 4 kilograms. And let's say that it is a total distance of 3 meters from that contact point. And then let's say that the bench is supported by a cable with some tension in it at an angle of 20 degrees. Okay, so the whole question is we want to be able to find what tension is. So this question is for Sophia, and then we'll do a gravitational ones incognito after. Hey, Jasmine. So does anyone know how we'd find out what the tension in our cable is? So again, I've got a computer sitting on my table. I've got tension at 20 degrees to the table. It's a cable, so this is my cable holding that end of the table up, and the table's attached to the wall here. Tips for practice for OCRA paper 1. So OCRA is actually really similar to AQA. So I don't think you're not in our lessons, are you? So there's quite a lot of OCR people in our lessons as well. You know how we've got cram courses as well coming up. But I would say for OCR and all the subjects, you just want to make sure that you're doing as many past paper questions as possible. So I don't know if you follow us on TikTok, but do you know on TikTok I've got BrookDoesPhysics. So I do loads of past paper question there. So I've done loads of them on thermodynamics, loads of them on gravitational fields, and loads of them in mechanics. So if you just go to the page, BrookDoesPhysics, and you can just search the word. So you do BrookDoesPhysics and then type in thermodynamics. It'll bring you up all the questions. Oh, they're helpful. I'm really happy to hear. Yeah, so good job. So what I want to do is I can resolve the tension. So I can figure out what component of it is going in the vertical direction and what component of it is going in the horizontal direction. So just going to change colors to see what we do now. So to find what the horizontal component is, we have to go through the angle, and the trick is to do it fast. Anytime you go through the angle, it's going to be t cosine 20. And if you go against the angle, or like you went against God, you committed a sin. Yeah, pranav, lovely. So that's going to be t sine 20. Okay. So I have to be able to find out what t is. So this is a question about moments. Okay. So moments I know is force times distance, but we have to remember it's the perpendicular distance. So I have to be able to figure out where am I going to take moments about to calculate what this tension is. So hopefully you're thinking, I'm going to take moments about here because I don't know what force is acting at that contact point. So that's the point that I'm going to take my moments about. So I'm going to take moments at that point X. Okay, other facts I'm told is the table is uniform. So what that means is that the center of mass, or we can say the weight, is going to act always at the center of mass. So the length of the table is 10 meters. So what I'm going to do is find where 5 meters is along from the point I'm taking moments about. And that's where I can say that my weight is going to act. And I know weight is the mass times the gravity. So it's 5 times by 9.81. Okay, so if anyone can give it a go, keep going. But as I keep adding points here, see if you can figure out what T is. So hopefully now you're thinking, I can't have the computer in kilograms, it needs to be a weight. So it's going to be 4 times 9.81, W equals mg to put into gravity. And then what I'm going to do is my rule of moments is my moments in my clockwise direction must always equal my moments in my anti-clockwise direction. So if I just go to purple now, so you can see where I'm going now that I've got all my facts on my table. So I'm taking moments about this point. What I want to do now is I would look at all my moments that's trying to pull it in the clockwise direction. So I can see I've got the computer. So the force of the computer is 4 times 9.81, and its distance from that pivot point is 3 meters. I've also got the weight, which is 5 times 9.81, and its distance from that pivot point is 5 meters. And that must equal all my moments trying to go in the other direction. So that's this one. So there's my perpendicular distance. So that's why I have to use t sine 20, because I need the force to be perpendicular for the distance from moments. So what I need to do is that distance away from point X, the whole table is 10 meters. So the distance of that from point X is going to be 10 meters. So it's going to be t sine 20 multiplied by 10. So hopefully now you can solve for t, so give it a go. Shreyas, you love Bubba. I love Bubba, obviously. I love Bubba. I think he's the most handsome little man. He's the most handsome little lamb. Does fire have a shadow? That's a good question. So how shadows work? Sophia is actually helping. Oh, I'm so happy it's helping. So hopefully what you're doing here is 4 times 3 is basically 12. So 12 times 9.81 plus 5 times 5 is 25. 25 times 9.81 is going to equal t sine 20 multiplied by 10. So to find what t is, all I have to do is divide both sides by sine 20 multiplied by 10, and that will give you a value of t then. So I'll give you a value of t. Okay, so the key thing about moments, it has to be force times the perpendicular distance. And the other key thing about moments, you always want to take moments from the point that you don't know any forces. So we know they're in contact here. There is some force here, but I don't know anything about it. So that I can ignore it, I take moments about this point. And then all I have to do is my force times my perpendicular distance. My force times my perpendicular distance. My force times my perpendicular distance. And this would be quite like a common style question for moments, because what they're doing is they're trying to get you as well to find tension. So you had to resolve as well. So again, we know if you go through the angle, it's always cosine, but that one is parallel. It has to be the perpendicular distance, which is why we had to use our t sine 20. So hopefully that was helpful, Sophia, and thank you for asking. Are there any massless particles? Yes, Jasmine. There's one called a neutrino. Have you heard of a neutrino? The queen deserves her knight in shining armor. What do you mean? Pranav, past papers. What do you mean in the channel? Do you mean in this session right now, or do you mean like in TikTok? Because in TikTok, they normally are past paper questions. A photon. Oh, so a photon technically is like a virtual particle. So a photon, what it is just a packet of light. So EM waves is a packet of light, of radiation. But a neutrino is the one that is massless. So I'll leave that up there now. But a neutrino is the one, hold on, let me find my pen color. Where have I gone? Bear with. Why can't I get the pen back on the, oh, there we go. Sorry, I was having a bit of a moment there trying to find the pen. So if you've heard of particles, you might learn that an electron has got zero mass, but actually an electron doesn't have zero mass. An electron does have mass. It's just a tiny amount of mass. I think it's times 10 to the negative 31 kilograms is what it has. So it's a tiny, tiny mass. But a thing called neutrinos, we represent like this. So they're called neutrinos. Neutrinos, they're the ones that have got zero mass and zero charge. And we actually didn't discover them until very late on. Fire having a shadow. Shadows are formed because light can't pass through an object. So the fire gives off its own light, right? So because it gives off its own light, it technically wouldn't have a shadow. Could you please go through a moments question from Isaac Physics called shelf and brackets? Do you mean shelf and this? Do you mean like this was a moments question here? Eater, do you see? Does this help you out? So this is the math we did there for a moments question, or let me know if you want another question on it. Noah, you're generally saving my A level. Thank you so much. Someone who does physics without maths. Oh, Noah, that's music in my ear. I'm so happy to hear. What do you mean? So you're not in our lessons, are you, Noah? So are you just watching them through TikTok? Is that what's helping? But yeah, so I do think doing A-level physics is quite hard if you don't have A-level math, because especially at the start, because all the math is very intense. The maths, sorry, is very intense. But over time, it'll get like easier and easier. So it's really good that I'm really glad to hear it's helping. Can I do a question on gravitational fields and antiparticles? I love antiparticles, so yes, I'll do one now. Just like how sun doesn't have a sun. What do you mean the sun doesn't have a sun? What are you talking about, Pranav? So Nathan, yeah, so we can talk about antiparticles and subatomic particles now for the universe. That's a good question. Are you watching the TikTok? No, I'm so happy to help. And then Noah, just remember, keep sending me a DM or write comments underneath them if there's topics that you want me to go over in particular, right? So then I can, when I plan the TikToks, normally what I do is I read your guys' messages to see if there's anything in particular you guys want me to revise. And then that's what I plan my TikToks on. So same with you, Pranav, if there's, let's say there's a past paper. So for example, say you looked at a past paper 2023, question 4, when you're revising and you no clue how to do it, just send me a message and say, Miss, can you do the AQA 2023 question 4 paper 2 question, and then I can do that on TikTok, right? So just send me a message what question you want me to do. Is this for year 12? So I've got a TikTok one for GCSE and for A level. So you can just message me exactly what you want me to do. And then that helps me, right? Because I want to make the TikToks helpful for you guys. So I've been picking questions that I think are hard, that I think will be helpful for you guys to revise before your mocks or for your exams. But again, if you see a past paper question that you don't know how to do, if you just shoot me a message or a DM or comment underneath a TikTok, then I'll see that and I can do one. Music EXO. You keep getting exam question wrong. So the problem with exam questions. So are you doing AQA, Music EXO? So if you do AQA 2019, 2022, 2020, and 2021, those past papers are really nice. So you want to feel good about yourself, do those ones. They're really good. But after COVID, so the 2022, the 2023, and the 2024 papers, those are mostly applied physics. So what that means is they wrote the question slightly different. You just had to figure out it's the same math. So the key I would say is read the question and figure out what topic it is. So for example, if the topic is on moments, then all you got to do is think about what math did you do in class, right? Because they still have to test that you have the same maths knowledge. So they're still going to test the same stuff. Do you know it's force times perpendicular distance? So the key thing is just reading the question and figure out what topic it is. How did you use that math in class? And then just trying to push it into one of those questions. AQA has been the hardest by far for the past 3 years, but it doesn't mean if you're doing AQA that you're going to get a bad grade, because remember, there still has to be a certain number of people who get A star and an A. So AQA has been the hardest the last few years, but roughly, it's around 65% to get an A star. Whereas if you do something like OCRA, I can't even write, OCRA has been easier the last few years. So the grade range is much higher. So you had to get a higher grade to get an A star. So yeah, AQA is harder, but I do think it challenges you better for university. So that's why our course online is AQA, because I think it's the hardest one. So if you can do all the AQA questions, you'll find the other exam boards much easier. Whereas if I had taught the OCRA spec, you'd find AQA really difficult and it wouldn't be as applicable for you. Gravitational and electric fields. Yes, so someone asked me there a minute ago about the universe question. So we'll do one on antiparticles, and then someone else asked me about gravitational fields acronym. So we'll do the universe one, and then we'll do the gravitational field ones. Mohammed, you can't get access to the 2024 paper. Only your school teachers have access to the 2024 paper. So you can ask your teachers if they can give you the past paper questions and give you access to it. But they might not, because a lot of teachers will use that paper as your mocks. So they don't want you to see it yet in case they use it as your mocks. Okay, so someone asked about the universe and particles and antiparticles. So the universe, the best theory right now, right? It's the theory, it's not a fact. The best theory right now is the Big Bang. Okay, so that's our best theory. The Big Bang is when we said that all energy, mass, and time was created. Okay, and all time, energy, and created with equal numbers of matter and antimatter. So matter and antimatter, equal amounts. Okay, and it's actually still a big topic of research, which is really interesting because we're not exactly 100% sure why our universe is made of matter. So basically, how come our universe is made of matter? Why did the matter win out? And one of the best theories that I've read about is that we think that they decay at different rates. So antimatter decays faster. So because it decays faster, that means there was slightly less of it in the universe at one time and slightly more matter in the universe at one time. So that means that anytime a matter particle like a proton collided with an antimatter particle like an antiproton, they're going to annihilate each other and produce 2 EM waves of energy, right? Because they annihilate each other. Because the matter and antimatter, they always have equal mass, but they have opposite charges. So if a proton is +1, what's going to be the charge of an antiproton? Oops, sorry. What's going to be the charge of an antiproton? Where'd it go? Oh no, I just deleted it. Oh, there it is. I'm having a moment. So a proton is +1. In the chat, do you know what the charge of an antiproton is? So they have equal mass, opposite charge. If proton's +1, clearly my antiproton is going to have a charge of -1, right? So again, what we think is our universe, yeah, Nathan, thank you. Yeah, good job. So what we think is our universe is mostly made of matter because antimatter decayed slightly quicker. So that's why our matter won out, okay? So our matter can be split up in different categories. So we've got things called hadrons, and we've got things called leptons. Okay, and you learn about this when you do your A-level physics. This is particle physics right now. So your hadrons can be split into 2 different categories again, your baryons and your mesons. And what you need to know is hadrons are always made of quarks. And what you need to know about leptons is your leptons are always the things like your electrons and your neutrinos. Remember we talked about earlier about a neutrino is the only mass, N-E-U-T-R, can't spell today, neutrino, N-E-U-T-R-I-N-O. Neutrino is the one that has 0 mass. Remember, you're 18 minutes late, you're grand. So then baryons are always made of 3 quarks, 3 real quarks, or 3 antiquarks, that's the rules. And then mesons are always made of 1 real quark and 1 antiquark. And that's how we write an antiparticle in physics. See how here a proton and an antiproton, I put that little line above it? Same thing in physics. An antiquark, we put that little line above it. Okay, so other things like leptons might be a muon. You might have an electron, neutrino, an electron flavor, a neutrino in the muon flavor. And if I want to write the antineutrino, we just put that little line above it. The antineutrino, we just put that little line above it. Antimatter has the exact same mass, just an opposite charge. So just a quick question then, because someone asked me about particles and antiparticles. A proton is a baryon. Can you tell me what are the free quarks inside a proton? What are the 3 quarks in a proton? Does anyone know? I just help you out, remember. The free quarks you know about is the up, down, and the strange quark. An up quark has got a charge of plus 2/3. A down quark has got a charge of minus 1/3. And a strange quark has got a charge of negative 1/3. Yes, Noor, good job. List blocks, good job. Aye, good job. Yeah, good job. Right, so we know a proton has got a charge of plus 1. So I need to get a charge of plus 1 overall. It's a real particle, so it's made of 3 real quarks. So think, how am I going to get 3 real quarks to get a charge of plus 1? So I've put 2 ups there. That's plus 2/3 and plus 2/3 gives me plus 4/3. That's too high. So I need to have a negative particle in there. So we put a down quark is negative 1/3, so which gives me overall charge of plus 1. And you have to remember, protons don't have any strange particles in them. So protons don't have any strange particles in them. James, do you have to remember this? You get given a data sheet in your exam, and your data sheet exam, it will tell you this little bit of information. However, this topic is very hard if you haven't learnt it. So I would highly recommend the thing that I've drew out here about matter and antimatter. I would highly recommend you just keep drawing this out like 10 times. Draw out until it goes in your head. Because questions like this, you want them to take you like 30 seconds in your exam. So in your exam, if it says, what's the quark size of proton? You want that to take you 30 seconds so you can spend all the rest of that time that you have trying to do the harder questions, not trying to look for your data sheet to find out what the charge of an up quark is. Yeah? Helpful? Music XO, slightly. Okay, so just to show you, let me get a piece of paper. Just to show you a difference. So in AQA, you do the double slit experiment. So I don't know if you guys have done this yet, but the double slit experiment, what it is that we shine a light source at the slits, and then the slits, you're like with me. What happens is that you're going to get diffraction. So the waves are going to interfere with each other, and then we're just a pattern on the screen. And the pattern on the screen is what you're going to have is right in the middle. It's called the center, so the central maximum. And then what happens is you're going to get these alternate dark and bright regions on either side. So alternate dark and bright regions on either side. There's an equation to learn this in A-level physics. And AQA, it's W equals Y times D over S. So W, what it means is how far away are these fringes from each other. So that's what W is. Y is what wavelength of light did we use to begin with. D is the distance between our slits and our screen. And S is your slit separation, so how far apart are these two? But if you do OCR, it looks slightly different. I think in OCR, bear with me, I'm pretty sure it's still, I'm having a blank. In OCR, I'm pretty sure, is it W equals YD over A? Is that right? AX over D. Nathan, yes, you know better than me, thank you. Yeah, it's wavelength equals AX over D. Yeah, you're right, thank you. So the capital D, so I'm just going to change colors so you can see how the OCR one is. So if you do a course, I have both data sheets with us all the time, so I can show you the differences, but it's mainly just this one. So wavelength is still the same. It's whatever wavelength of light we're using. Capital D is still the same. It's the distance between your slits and the screen. A this time here, A is what we call the distance between your slit separation, and X is what we call W here. So you can see if you rearrange this, you get the same equation. So what I can write is wavelength times D is equal to A times X, or wavelength times D divided by A gives me X. So you can see how those equations become the same, that X in OCR is equal to W in AQA, and that A in OCR is equal to X in S in AQA. Yeah, so this is Young's double slit experiment. Umar, for this one, no, you don't need to be able to derive this one. For this one, you just need to be able to apply the equation. Oh, Pranav, I love that you think that I would know what's on the other side of the black hole. But again, what's fascinating about physics is that you do learn about black holes in astrophysics if you do the astrophysics topic for AQA, right? You do learn loads about it, and it's fascinating. But something that's really cool about A-level physics is you learn the peak of our knowledge, right? We're learning the stuff that we don't know much more about yet, right? So black holes, they were only imaged not that long ago, right? Even though we didn't know about them. So black holes, what we know is that nothing can escape them, right? They suck in everything. One of the theories is that at the other end of a black hole is a thing called a white hole. So this is my black hole that sucks in everything, not even light can escape. At the other end, we think a theory, so remember it's a theory because we don't know, might be a white hole where all that light comes out, and it might give us a multi-universe. So it's called the multi-universe theory if you want to look at it. It's like when we think there's more than one universe that can exist. Minato, you want to do A-level physics? Yes. Yeah, multi-universe. Okay, so someone asked me about gravitational fields and electric fields. So gravitational fields, what could we do? Let's say we got Earth. It's a common question as well. So here's Earth, and I can get my data sheet for our time. We've got 4 minutes, but we got Earth and we got a satellite. We'll just make up numbers then. That's a terrible looking satellite, but this is my satellite. And my satellite is going to be orbiting the Earth. Okay. I want to figure out what is the force of attraction between the satellite and the Earth. So we know to Newton's third law that the satellite is pulled by the Earth due to gravity. The Earth is pulled by the satellite due to gravity. And we can calculate the force, which is going to equal G, the universal gravitational constant, times the mass of the Earth, times the mass of the satellite, over the distance between them squared. Okay. Key thing here is, and people always forget, is that what they want to do is they try to use whatever orbital height the satellite's at for R. Okay. But that's not the R you use in this equation. You have to remember that you have to include the distance from the center of the Earth. So when you get these questions, people always lose marks because they forget to include the radius of the Earth. So what R actually is it's going to be whatever height our satellite is above the center of the Earth, and you have to add on whatever the radius of the Earth is. So what R actually is, again, is whatever height our satellite is above the center of the Earth, and you have to add on what the radius of the Earth is, and you square that whole thing. That's what people normally forget to do. Someone said there about gravitational potential is negative. Yes, that's a good question. So let's say again we got our Earth, okay, and we're going to have these gravitational potential lines around the Earth. So if you're doing your GCSEs, this might be a bit much for you right now, but you've got these gravitational potential lines around Earth, okay? So what we know is gravitational potential. So gravitational potential is the amount of work done required to bring a mass from infinity to a point in that field. Okay. So we know at infinity, that's always going to be our zero energy, our 0 joules. Okay. So it's like something like unbound. It's free. Okay. So the gravitational potential is the work I have to do to bring a point mass. So let's say I got a mass here of 1 kilogram. How much work do I need to do to bring that mass from infinity to some point in this field? Okay. I know that gravitational forces are always attractive, right? So the Earth will pull that mass in anyway, right? Because gravitational forces are always attractive. Okay. It's because it's always attractive. So we don't have to actually put any work in for this mass to get pulled in there. It does it itself. So because if I have to input work, that's a positive number because I have to input work to the system. But because it's attractive force and it pulls it in anyway, that's why it's going to be a negative work, because technically energy is it's losing energy by going towards there. So that's why all these lines become more and more negative, because it's an attractive force. Same thing when you do electric fields, just to finish that off. Same thing when you learn electric fields, we know that the potential is the work done per unit charge to bring a positive test charge from infinity to some point in the field. So if I have a negative isolated sphere, all of the potential lines around it are going to be negative as well, because that's going to be an attractive force. But if I have a positive point charge, all the potential lines around it are going to be positive because I have to put work in to bring that positive charge towards it, because they'll want to repel each other. I have to put work into the system to get there. So around the positive one will be positive numbers. Yeah. Guys, that was like an awesome, what was that? We had a wee half an hour there, eh? That was brilliant. And thank you guys for all your questions and like joining us. Engineering, science, and astrophysics. In astrophysics and engineering science, you normally do the first year, you normally do the same stuff. So again, I know I didn't answer all your questions, but I know a lot of you asked me about gravitational fields there, electric fields. We did a whole moments question. We did a whole thing on particles. So we actually did like quite a lot there in 30 minutes. So that was great. It was helpful. I'm really happy to hear. So hopefully I'll see you guys next week as well. So just remember on TikTok, just send me a message or DM or comment underneath the past paper questions I've already done if there's something you want me to do again or something you didn't understand, so I can help you guys out a bit more, right? Because that's the point of it. Or if there's anything you want to do in these lessons. Yeah. So it was great chatting to you. Pranav, thanks for coming. Thanks, Fahim. Thank you, Joshua. Sophia, thank you for earlier. Nathan, thank you. See you later, James. Oh, James, we'll do that next day, just because I have an actual lesson now. So I'm teaching Key Stage 2 now, so I am. But yes, thank you. That's very helpful. Pranav, see you this evening. What do you mean? How will you see me this evening? Please don't creep me out. Why will you see me this evening? I'm teaching Key Stage 2. You know, at GCSE? I was like, are you trying to come to my house here or what's the crack? Right, I'll see you later. Have a lovely day. Hopefully see you all next week.